Hello students, welcome to revision of a chapter Haloalkanes and a Haloarene. So basically in this topic, in this revision session, what I am going to discuss, I am going to focus first on IUPAC nomenclature of Haloalkanes and Haloarenes, that is this. Second, chemical reactions or preparations of haloalkanes. Third, I am going to discuss about a chemical reaction or a chemical properties, chemical reactions of haloalkane. Fourth, I am going to discuss about preparation and chemical reactions of haloarene. So to start with, here the chemistry is about haloalkane. Haloalkane means what? Halogen connected to alkane, and haloarene means what? A halogen connected to arene. This is what it is, right? So we'll start with the IUPAC nomenclature. IUPAC nomenclature, if I have a structure this way, CH3, CH, Cl, CH2, C double bond, CH2. Now, any IUPAC name, okay, this rule is common to anything, okay? Any IUPAC nomenclature you are doing, this rule is rigid. All the rules, all the guidelines of the IUPAC nomenclature should be organized around this one rule. Remember this rule. If you follow this rule, you will never go wrong for a IUPAC nomenclature. That every IUPAC name includes what? A prefix. There is a prefix. Then after that prefix, you will write about a word root. Then after word root, it is primary suffix. And after primary suffix, it is a secondary suffix. So this should be the order. You will never go wrong. So prefix, what does the prefix tells you about? Prefix tells you about position. It is telling you about the position of substituents. What does the word root tells you about? Word root tells you about number of carbons on parent chain, right? Primary suffix tells you about position of double bond or triple bond, and secondary suffix tells position of functional group. Okay, it is this simple. So over here you see there is a substituent. One chloro is a substituent, right? And numbering should be done in such a way that, always remember this order. Numbering should be done in such a way that always a functional group should get a lowest number. If there is no functional group, then it is a double bond which should get a lowest number. If there is no double bond, then triple bond should get a lowest number. And if triple bond is not there and all these things are not there and only substituents are there, then you will be applying a rule that that substituent should get a lowest number. Then you will apply lowest set of locus and all these things. Then last is substituent. So this is the thing to remember, like priority to give lowest number. This is a thing, priority to give lowest number. Priority to give lowest number. So in this case, numbering will start from here. 1, 2, 3, 4 and 5. It is 4 chloro. This is prefix. Since there are 5 carbons on a parent chain, it is what? Pent, right? And first position is the double bond. So 1 ene. If there was a functional group, I would have replaced this last e with a suffix of that functional group, right? So I am keeping this as it is. So one more example will do. If we have an example this way, CH3, CH, and Br is there, right? From where you start the numbering, again double bond should get the lowest number. You start from here. So 1, 2, 3, 4 and 5. What are the prefixes? What are the prefixes over here? There is a methyl and a bromo. There is a methyl and a bromo. On what position? Fourth position. So B comes first in alphabetical order. So you are writing 4 bromo, 4 bromo, 4 methyl, 4 methyl. Done. Prefix is done. Then word root is what? There are 5 carbons on a parent chain. So word root will be a pent. Pent. And the position of the double bond is on the second. So 2ene. That's it. Okay. Now draw the structure. The question may be what, draw the structure. Draw the structure. Name will be given. You need to draw the structure of that. So over here it is given 4 bromo, 3 methyl, pent, 2ene. So 4. This is the name which is given. 4 bromo, 3 methyl, pent, 2ene. Now how to write a structure of this? There are 5 carbons. We can see that there are 5 carbons on a parent chain because it is written pent. So we'll write that 1, 2, 3, 4 and 5. Okay. Now talk about a substituent. There are 4 bromo. Like if you are numbering this, you start from any side. Let's say 1, 2, 3, 4, 5. Okay. You should start from a side. Let's say you are doing it from here. 1, 2, 3, 4 and 5. You see that on second, 2ene, right? Double bond is on a second carbon. So double bond is over here, second, right? And 4 bromo. 4 bromo is what? Here there is your 4 bromo. And third position, there is a methyl. Means here this is your third. So 1, 2, 3, 4 and 5. Done. Now you put rest of the hydrogens over here. How many hydrogens will be required? 3. Here you will require just 1 hydrogen. Here you don't require a hydrogen. Here also just 1 hydrogen. So this is a name, this is a structure of the haloalkane which is asked over here. Now write the IUPAC name. There is one more compound which I'll do. The structure is given this way. Structure is given this way. This is weird. How to name this? Okay, you see this. This is a bond line structure, and how to write a bond line structure. And like this is a carbon. There is a carbon-carbon double bond. Means this is terminal is also carbon. This is also carbon. This is carbon. Here it is Br, and here it is carbon. So now rest of the thing is that you need to put a hydrogen. You are going to put a 3 hydrogens over here. 3 hydrogens. Yes, no, 1, 2, 3, 4, and this is already 4 bonds are there. Here 3 hydrogens, here 1 hydrogen. Now you see the longest chain in this case. You see that longest chain is this. This is a carbon 1, this is carbon 2, this is carbon 3, carbon 4 and carbon 5. Why I started numbering from here? So that double bond gets the lowest number. So these are the 2 substituents. One is at a 4th position and one is at a 3rd position. The bromo, which comes in the lowest alphabetical order, the name will be 4 bromo. I am writing that first. 4 bromo, 3 methyl, yes. Then how many carbons on a parent chain? Okay, here also there are 5 carbons, so it will be just pent. What position is the double bond? Second. So 2ene. So this is the thing about the IUPAC nomenclature. Here we'll do the revision of the preparations of the haloalkane. So we'll take question and we'll understand the chemistry of preparations of the haloalkane. So question asked is write an equation for preparation of 1 iodobutane from 1 chlorobutane. You know, there are something called as halogen exchange reaction. There are halogen exchange reaction. Halogen exchange reaction. Exchange reactions. There are 2 halogen exchange reaction which you are learning in your syllabus. The first is Wilkinson reaction. Okay, and second you are learning is a Swartz reaction. Swartz reaction. Like this reaction is for specific, these reactions are very specific. This reaction is specific for preparation of what? Preparation of iodoalkane. Okay, and this reaction is specific for preparation of fluoroalkane. Okay, keep this in mind. So Wilkinson reaction is what they have asked about this. So general thing is like Rx plus sodium iodide. This gives you Ri plus NaX. So what you are getting? Iodoalkane over here. Iodoalkane. You are getting iodoalkane. Means what is happening? The halogen is just getting exchange over here. Iodine is coming over here. Halide is going with the sodium. That is the thing. Over here, Schwarz reaction is also similar. But over here, what we use is a silver fluoride. And here also there is an exchange. Rf and AgX. So this is a Schwarz reaction. But they have asked about iodobutane from a chlorobutane. Means reaction will be this way. It is very simple. You write a chlorobutane, CH3, CH2, and one chlorobutane. The name of this 1, 2, 3, 4. So name of this is 1 chlorobutane, right? 1 chlorobutane. You react this with what? You react this with a sodium iodide. So halogen exchange reaction is going to take place. Halogen exchange reaction is going to take place. And what you are going to get is CH3, CH2, CH2I plus NaCl salt. So this compound is 1 iodobutane. So with this example, what we can understand that we have revised two reactions. One is Wilkinson reaction and Schwarz reaction. See, whenever you learn organic chemistry, always compare the reaction, how one reaction is different from the another. Okay, that is the best, one of the best way to learn organic chemistry. When you compare and learn, okay, what is the common thing between this and that reaction? What is the similarity between one reaction and the other reaction? What are the differences between these two reactions? It helps you to keep the track of the reactions because there are so many reactions. Okay, so it is always to find some similarities and differences between the reaction, and that is how you can proceed ahead. Okay, next question we'll do. Okay, the question is thionyl chloride method is preferred for preparing alkyl chloride from alcohol. Give reason. Now, you know, whenever any reaction takes place, it is not that the only one product is formed. There are certain byproducts are also formed, and you require some cost, you require some efforts to separate those byproducts also, right? And let's say that main product is in certain state. Let's say main product is in the liquid state and byproducts are in the gaseous state. Then what will happen? The byproduct will evaporate and can be collected in some other container, or it can just escape the main reactant if the byproducts are in the gaseous state and your main product remains in the vessel, right? So similar kind of story, similar kind of thing happens with this reaction. Like if you want to prepare like general reaction I will write. Let's say alcohol is there. This is alcohol and you are using a thionyl chloride. This is a thionyl chloride. Okay. SOCl2 means what? Thionyl chloride. THIO. Right. What do you get is RCl, HCl and sulfur dioxide. This is a gas. This is a gas. Now higher alkenes like butane, chlorobutane and all, they will be in the liquid state. Okay. So this will be in liquid state. So what happens? The other reactant just escapes the reaction mixture. Like for example, if we take an example like this, if we take this example CH3, CH2, like this is what? Butane 2 all, right? If you react this with a thionyl chloride SOCl2, what do you get is CH3, CH2, CH2, CH2Cl. This is a liquid plus HCl gas plus sulfur dioxide is a gas. So reason for this should be writing that the byproducts, what is the reason? The reason byproducts obtain in this reaction are in gaseous state. Therefore it becomes easy for separation of main product from mixture. That's why thionyl chloride is preferred to prepare a haloalkane. Like this is that haloalkane which which is like this will be a 1-chloro-butane. Yes, one more thing to learn. You see that I am writing butane 2-ol. I don't write 1-hydroxybutane because over here alcohol is a functional group and chlorine is a substituent. That's why chlorine comes in a prefix and alcohol comes in a secondary suffix. Like there are no prefixes, so name starts with a word root, that is but, right? There are no carbon-carbon double bond, so just A-N-E, and last E of the primary suffix is replaced with a position of the functional group. So sorry, this is butane 1-ol. This is butane 1-ol, not 2-ol. I'm not mistaken. Write the major product of the following. They have given this reactant, and you are adding a substitution. Means this reaction will go via substitution. Now how to identify this? See, this is bromine and it is written UV light, right? Remember that if this is given, then it is free radical halogenation. Remember this reaction, characteristics of this reaction is free radical halogenation. Right, this is first point. Second, it is a substitution reaction. These are the points for you. This is nothing to write in an exam paper. Okay, this is substitution reaction. And substitution reaction means what? Substitutes. Like here, halide substitutes what? Substitutes hydrogen. Now, which hydrogen I'll tell you. You have to decide that. Then reaction goes via formation of free radical. Reaction goes via formation of free radical. Okay. Now over here, which free radical, like where the substitution is going to take place. Now the possibility is that you can see there are hydrogens over here also. Is it going to replace this hydrogen or this hydrogen or this hydrogen, right? So always remember that if it is doing a substitution over here, it is impossible over here. Why? Just imagine that there is a free radical formed over here. Okay, I'm just writing the possibility, not the final product over here. The possibility I'm writing CH3. Let's say one of the hydrogen. There are hydrogens, no? It is going and free radical is created over here. This free radical is most unstable because any intermediate, whether it is a carbocation, carboanion, or a free radical directly being present on a pi bond is most unstable. So this replacement of the hydrogen is never going to take place in this. So whenever it is a free radical halogenation, it will always be happening on what? Alkyl, either here or here. So the possibility is that I can have one free radical, I am removing one hydrogen, I am putting a free radical over here, and the other possibility, these are not a final product, intermediates I am writing. The other possibility is this. CH2 free radical. So instead of CH3, CH2 free radical. Now among this is the two possibility. Among this, which free radical is most stable? Remember that this free radical is in conjugation, pi, sigma and free radical. Over here, this is not in conjugation. It is pi, sigma, sigma and free radical. So this free radical is least stable. This free radical over here, free radical is less stable, and this is more stable. So finally the Br will be also coming, like homolytic cleavage takes place, no? Homolytic cleavage takes place over here, right? And Br is also coming as a free radical. Now free radical and that free radical will form one bond. So this will lead to the formation of this product, CH, Br and CH3, and this is NO2, and this will lead to the formation of this product. Okay, but this is minor product, this is minor product, and this is major product. So if it is asked, then you should be always writing a major product. So your answer becomes this. This is your answer. Free radical halogenation. Okay. One more thing, students, since I have discussed about a free radical halogenation, there are two kinds of halogenation. In the whole chapter, there are two kinds of halogenation. Halogenation means what? Substitution of the halogenation. I'll break up this because you are going to learn this further. Halogenation means what? Substitution of halogen. There are two kinds of halogenation. One is free radical, which you have now done just now. Free radical halogenation. Okay, and then there is a one more electrophilic substitution. Okay, so what is the difference between free radical halogenation and an electrophilic substitution? See, in both the cases, we are substituting a halogen. We are substituting a hydrogen with halogen, right? But the approach is different. Over here, this is an electrophile. Here, Br plus will be there, and here Br free radical will be there. Both will be having a different approach. Like for that same example, if I ask you for that same example, like here it is this CH2 CH3, okay, and if you want to do a let's say this is a NO2, okay. So over here, if you do the bromination, free radical halogenation, like you understand this from this UV light and bromine that it is a free radical halogenation. You get a product getting substituted over here, Br being getting substituted over here. Like I will write the major product only, Br getting substituted over here. Further in this chapter, you learn about the electrophilic substitution on a haloarene, right? But we'll not take a haloarene. I'll just explain you the general concept over here. Okay, let's say this is your NO2, and this is your CH2 CH3. Electrophilic substitution, right? The Br plus, where this Br plus is electron deficient, this ring is electron rich. Like this is meta directing to an incoming electrophile. So where this Br will go, like meta position of this is a meta position, right? So it will attack over here, and a substitution of the Br is getting on ring Br and NO2. Understand the difference. In electrophilic substitution, the Br will get substitute on a ring, and a free radical, it will get substitute on a hydrocarbon chain. That is what is the major difference between these two reactions. Anyway, you are learning this in a haloalkane. You are learning this in a haloarene chapter, haloarene topic. I mean, not chapter. Like next section. So here is the reaction. Like they have given PCl5 and this is a alcohol. Okay, so see, remember that PCl5, what to know about a PCl5? PCl5 is a good source. Why we are adding PCl5? It is a good source of Cl minus. It is a Cl minus. It can give away its Cl minus very easily. You can see this phosphorus. What is the structure? Too many bonds on this phosphorus. So Cl can break apart very easily. Like too much of the hindrance is there. On top of that, there are a lot of lone pairs over here. Three lone pairs on each of the chlorine. Right? You can see this. So there is repulsion, so this can break away very easily. So this is a good source of Cl minus. Now it's very simple. There is a Cl minus, this is negative, where it is going to attack or where it is going to donate its electron, where there is a deficiency of the electron. Now which carbon over here? You see that this is also a carbon, this is also a carbon, this is also a carbon, here also there is a carbon and carbon. So many carbons are there, but it is going to attack on this carbon only, because this carbon attack means what? It is going to donate its electron to that carbon. Means it is going to form a bond with that carbon. New bond it is going to form. Why? Because this carbon is connected to oxygen. What is the nature of the oxygen? Oxygen is what? Oxygen is electronegative. Electronegative in nature. What is the meaning of electronegativity? Electronegativity means tendency of an atom to attract share pair of electron towards itself. Means this oxygen which is there, no, it will pull the electron of the carbon also towards itself. So in that case, there is a partial negative and this carbon is partially positive. That's why none of the carbon, if you compare other carbons, they are not as partially positive as this carbon. So the attack or donation of this chlorine takes place on this carbon only. Now the longest bond is going to break. So carbon oxygen is the longest bond. This is the bond which is going to break. So what do you get? A major product over here is CH2Cl plus byproducts you will be getting POCl3 and HCl. Okay, these are the byproduct, but this is the major product. You should be writing this. Sorry, this is not a benzene. This is not a benzene. Sorry. Cyclohexane it is. Okay. So next question is what will be a major product? What will be a major product? HBr. So this is a reaction. Okay, you can think of this reaction. This reaction is again a preparation method for what? Haloalkane. Yes. This reaction is known as Markovnikov's reaction. Okay, this is a reaction known as Markovnikov's reaction. According to this, what is Markovnikov's reaction? Negative part of the adding species, I'll write over here, negative part of adding species goes to that carbon, having less number of hydrogen in carbon-carbon double bond. This is rule. There is a mechanism, but you don't have to go to a mechanism. So over here, this is a carbon which has a less number of hydrogen, just one hydrogen. Here this is having two hydrogens. So across this double bond, and the positive part will go to the carbon which has more number of the hydrogen. So H plus is a positive part. See, if you ask me, Br minus is negative part of the HBr and H plus is a positive part of the HBr. Right? So what is this? The compound what you are going to have over here is CH, Br, and this is CH3. Right? So this is according to the Markovnikov's rule. I mean, Br gone over here, hydrogen gone over here, so that CH2 is converted to what? CH3. Hello students, let's revise chemical reactions of haloalkanes. So chemical reactions, we write the heading, chemical reactions of haloalkanes. Here we are going to learn about two kinds of reaction. One is substitution reaction, and other is elimination reaction. Okay, so substitution reaction, there are two kinds. There is SN1 and the other is SN2. Okay, we'll discuss this in detail, but how to identify a given reaction is substitution reaction or a elimination reaction. So we'll discuss this. I'll write the alkyl halide. Alkyl halide is this. Let's say this is the alkyl halide, CH3, Cl is there. Okay, and here there is CH3, and you put NaOH. It is a base which is aqueous medium is aqueous. So what is going to have, what will be a product over here is that the OH minus is going to attack on this carbon and form a new bond, and it will break an older bond. Like if I were to show this attack, OH minus will attack over here and this bond will leave. Why only this carbon? Because this is negative and this carbon is partially positive because of the presence of this electronegative element, right? So that's the process, and this is how the reaction goes. CH3, CH2, CH, and here there is OH and CH3. This is general way of representing a substitution reaction. Now, same reaction, like similar alkyl halide. So I'll write over here substitution reaction. This is substitution reaction, right? Now if there is a compound, same compound I am taking, but only instead of I take a base, a strong base like potassium hydroxide, okay, I can take a NaOH also. It can be NaOH also, any base, but the medium is alcoholic. Okay, medium is alcoholic. So elimination means what? Let's talk about this. You remove this hydrogen and Cl and make a double bond over here, or either you remove this hydrogen and this Cl and make a double bond over here. That is what the elimination, no? So this is what is elimination reaction. The difference is that you have to identify the reagents. Like for example, they may give you a KOH and plus ethanol means what? KOH plus ethanol means what? Ethanol is alcohol. Okay, they may just write NaOH with alcohol, KOH with alcoholic medium. Sometimes they may not mention also that alcoholic medium. They may mention some alcohol. Right, so you have to identify what is the thing. So elimination, if A is eliminated means A and H and Cl is eliminated, double bond will be formed over here, and H and Cl will be eliminated and double bond will be formed over here. So there are two possibilities of the alkene in this case, right? So I'll write both the possibilities, CH and CH3, and the other is CH3, CH2, CH and double bond. This is major product, this is minor product. Okay, why this is minor product? This is according to Sadzev rule, more the number of the alkyl groups on either side of the double bond, more stable is the alkene. So identify when particular reaction is going to undergo a substitution reaction and when some particular reaction is going to undergo a elimination reaction. So elimination reaction which is there, this is also called as a beta elimination. Or we call this to be dehydro, means removal of hydrogen and removal of halogen. So dehydrohalogenation, right? So the difference is you should know what is NaOH, what is that medium, aqueous, then substitution means only chlorine will be replaced with OH, and in that case you get a product as a alcohol, and over here in this case elimination you get a product as a alkene. Okay, very simple it is. So now we'll go into the depth of the substitution reaction. There are two kinds of reaction. One is SN1. It is also called as a substitution nucleophilic unimolecular, or else I will write, I'll divide this board into two and I will write separately. So SN1 will compare this to SN1 and this is SN2. So this is substitution nucleophilic unimolecular, and this is substitution nucleophilic bimolecular. Means substitution. What we are doing, we are learning the chemical reaction of the alkyl halide, right? We are learning chemical reaction of the alkyl halide. Over here, first difference I will write, this is a two-step process. This is two-step process. This is two-step process. This is one-step process. One-step process. Okay, this is the main difference. And two-step means what? Like for example, this is favorable. First I will write. Second is this is favorable for tertiary alkyl halide. Like tertiary alkyl halide goes via this mechanism, and over here this primary alkyl halide, this is primary alkyl halide. Like for example, if we have a alkyl halide like this, CH3 and CH3 and Cl, and you want to do a substitution. First step is that step one is formation of the carbocation. Means there is a conversion of this to this. Most stable carbocation will be formed, and then step 2, space is less, I will write over here step 2, attack of nucleophile. This is the second step, attack of nucleophile. Okay, hope that is coming into the frame. Yeah. So over here I'll write very small, just see CH3 carbocation, and that is OH minus was the nucleophile from the NaOH. This will give me alcohol. Many things are there involved, like a racemic, racemic product, then 50% and all these things, but this is what a reaction steps I am going to show. Right? Two-step reaction. This is one-step reaction. Primary alkyl halide example is this CH3Cl. Like this is primary alkyl halide. Means over here halide is connected to carbon, this is further connected to only one carbon. Here OH minus will come from the side opposite to that of leaving group, and finally directly you are going to get a alcohol. Right? So these are the SN1 and SN2 processes briefly discussed. Okay, next question will take, which of the following, question is, which of the following would undergo SN2 reaction faster in following pair. Okay, example is given this way: CH3 CH2 Br, and other is this way. Right? SN2 reaction faster means what? In which case It will be like this is primary alkyl halide. You can see this is primary alkyl halide. How do I understand it? Halide is connected to this carbon. This is further connected to only one carbon. This halide is connected to this carbon. This is further connected to 3 carbon. So this is tertiary alkyl halide. So SN2 means what? It is always a secondary. It is always primary, which is more favorable. So the answer is this. Next question is, what happens when 2-chlorobutane is treated with aqueous KOH? Right. Question is, what happens when 2-chlorobutane is treated with aqueous KOH. Now 2-chlorobutane. First you should know how to write a 2-chlorobutane. This is 2-chlorobutane. You have taken KOH, right? And it is aqueous. Many students make mistake. Okay, KOH means elimination, because in NCERT it is given KOH and in bracket it is written alcoholic, right? KOH aqueous will lead to what? It will lead to a substitution reaction, means OH minus will attack on this, and what will be the thing? Sorry, substitution reaction. So OH is going to, like, you are going to get alcohol, that is butane to all. Butane to all is the alcohol, and this is your 2-chlorobutane. Right? So next question is, what happens when 2-chlorobutane, same question, what happens when 2-chlorobutane is treated with potassium hydroxide in the presence of alcohol, means the reaction is very simple. 2-chlorobutane, you take a 2-chlorobutane, and react this with KOH in the presence of alcohol. Did not mention which alcohol, but sometimes they may write, in the presence of ethanol. You have to understand that it is an elimination. The major product will be this. You will be eliminating this HCl. So that double bond is formed in between. So this is the alkene which will be formed over here. So this is the major product. Okay. If the Cl was over here, there would have been only one product possible. Okay, if Cl was over here, then only one product, that is but1-ene. So here this is 2-chlorobutane, and what you get is but2-ene as the product. This question. Okay, before I go with this question, let's understand what is optical activity. Optically active compounds. Okay, how to identify optically active compound? If there is like optically active compounds, means the compounds which are able to rotate or change the direction of the plane polarized light, right? Like that is what the optically active compounds. How to identify that? Optically active compounds are the compounds which has a chiral carbon. Which has chiral carbon. What is the meaning of chiral carbon? Chiral carbon, or we say asymmetric carbon. Asymmetric carbon. Now asymmetric carbon means what? Asymmetric carbon means what? Carbon with all four groups attach. All four, or different carbon with all four different groups attach. Like for example, if I write CH3, 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 chlorine, CH3 and OH, Cl, and let's say this is the hydrogen. You see that among all this carbon, this is the chiral carbon because it is chloro, methyl, hydrogen, and this is completely different group. None of the carbon is chiral because there are 3 hydrogen which are similar. On this carbon there are 3 hydrogen which are similar. On this carbon there are 3 hydrogens which are similar. On this carbon there are 3 methyl which are similar, right? So only one chiral center over here or a chiral carbon over here. Now more examples we can take, like for example, is there any chiral carbon in this? Okay, there, like this structure is given, means this is a carbon, this is 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 carbon, right? So what we can say is that here there is hydrogen, here there is hydrogen, 2 similar groups, no chiral carbon. There are 3 hydrogen, 3 similar groups, no chiral carbon. Here there is hydrogen, here this is methyl. This is different, but this group and this group is one and same. So there is no any single carbon which is chiral. So chiral means what? All the 4 groups attached to it should be different, right? For example, we can write, in this case we can write over here, now this is the hydrogen, this is methyl, and this is a chiral carbon because this group is different, this group is different, this group is different, this group is different. That's it. So understand the meaning of a chiral carbon. Now question is given. We'll focus on the question which is given over there. Okay, 2 bromopentane, 1 bromopentane, 2 bromo, 2 methyl butane. Okay, write the compound which is most reactive towards SN2. Write the compound which is optically active. Write the compound which is most reactive towards beta elimination. Now we'll first write the structure 2 bromopentane, how it will look. Pentane means what? 1, 2, 3, 4, 5. 2 bromopentane means here is the bromo. If you start numbering from this side, CH2, 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 CH3. This is 2 bromopentane, right? Then 1 bromopentane is this. 1 bromopentane is this, CH3, CH2, 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 Br. This is 1 bromopentane. Then 2 bromo, 2 methyl pentane means there are 5 carbons on a parent chain. 2 bromo, sorry, it is butane, yes. 2 bromo, 2 methyl butane. Like here there is this is the hydrogen. 2 bromo, 2 methyl butane. Now the question is, first is write the compound which is most reactive towards SN2. Now over here if you see, this alkyl halide is secondary alkyl halide, right? Secondary alkyl halide, right? Then this alkyl halide is primary alkyl halide, and this alkyl halide is what? Tertiary alkyl halide. This Br is connected to this carbon, this is further connected to more 3 carbon. I will call this to be A, this is to be B, and this is to be C. So what is the answer for this? Okay, you can comment what is the answer, A, B and C. So write the compound which is most reactive towards SN2. SN2 means what? Primary alkyl halide. So option B, this is primary alkyl halide. So answer over here is option B. Write the compound which is optically active. You see that there should be at least one chiral carbon for the compound to be optically active. Like this is that this is the only carbon which is chiral. This is Br, this is hydrogen, this is methyl, and this is propyl. All 4 groups attached to it are different. So this is the chiral carbon. So this compound is optically active. What about this? There are no chiral carbons in this, there are no chiral carbon in this also. You see, this is a Br, this is CH3 and this CH3. These 2 are same, right? And rest, there are hydrogens which are similar. So these are also not a chiral. So only one. So here answer for this will be option A. Okay, here I am written B. Write the compound which is most reactive towards beta elimination. Among this, which will be most reactive towards beta elimination? The compound, which is the compound which will be most reactive towards beta elimination? That compound which gives most stable alkene. It is that compound. It is that compound. Answer for this is compound that gives most stable alkene. Okay, compound that gives most stable alkene. Now you think of this. We'll write a most stable alkene of this. So CH2 means one hydrogen over here. We'll remove this. Will not remove. That will be a minor product of this. It will give me a alkene this way. CH3, CH2, CH double bond, CH3. Here you remove this Br, means I will write it this way, Br, one and same, and this hydrogen I am writing this way. So what is the alkene you are going to have? CH3, CH2, CH2, CH, CH2. This is the alkene which you are going to have. Hope that is coming, yes. And over here if you see which alkene, like this is the hydrogen and this is the thing. So what is the alkene you are going to have? CH3, CH double bond, C, CH3 and CH3. Among this is the most stable alkene because it has maximum number of the alkyl group. Here there are just one alkyl group. Here there are just two alkyl groups, right? So maximum number of the alkyl groups on the either side of the double bond, most stable is the alkene. So option C will be the answer. Option C will be the answer. So next question is prepare butane using chloroethane. How you are going to prepare? See, there is a reaction called as a Woods reaction. Woods reaction. Woods reaction. It is a reaction of the alkyl halide. 2 moles of alkyl halide we are doing. Like sodium, 2 moles of alkyl halide, 2 moles of sodium. In the presence of dry ether, you get this way, 2NaX. Right? So it is this reaction with the metal, Woods reaction. Reaction of the alkyl halide with the metal. So chloroethane, CH3, CH2, Cl. This is chloroethane. You are reacting this with a sodium, 2 moles. You take this 2 moles and a dry ether. So what you are going to get? A R getting connected to another R. Means this is one of my R. This is getting connected to another R. So what is this? This is a butane. Right? So answer is prepare butane. So this is that reaction, Woods reaction. Next is, what would be a product? Next is, write the major product. Write the product obtained when 2-chloropropane is reacted with sodium, okay, with sodium in presence of dry ether, in presence of dry ether. Now for example, 2-chloropropane, how it looks? 1, 2, 3. Here is chloro, here it is CH3, H and CH3. You take this 2 moles and in the presence, you react this with the 2 moles of sodium in the presence of dry ether. What is the rule? This is a Cl, you will remove this. This is a Cl. So one of the R will connect you with another R. Means over here, a trick is this CH3, CH, CH3. From here, another R will be getting connected from halide which is there. So what is the name of this? Right? What is the name of this? You see, this is the longest chain. Right? And these are the 2 substituents which are there. You number them 1, 2, 3 and 4. So what would be a name? 2, 3 dimethyl butane is the name of the compound. So these are the reactions, like how haloalkane reacts with the sodium. So these are the different reactions we have learned so far, and this completes the revision of the reactions of the haloalkanes part. So next we'll discuss haloarene. Thank you. Hello students, in this lecture we are going to learn a concepts related to haloarenes. Okay, we'll learn the preparations method as well as we'll revise a chemical reactions related to haloarene, right? So what is a haloarene? Simple terms, halogen connected to the aromatic ring, and in your syllabus only aromatic ring which we study is a benzene. So benzene connected to halogen. So here there is a first question, aniline, convert aniline to what? Bromobenzene. Means the conversion is asked for this. Conversion is asked for this. Aniline you need to convert to bromobenzene. Now how this conversion could be carried out? The thing is that first we convert a aniline to benzene diazonium salt. Okay. See, remember this bond is very difficult to break because of the resonance. Okay, partial double bond character will be also formed over here. Direct substitution of the Br is not possible over here. So what is first done is this, a primary aromatic amine. Okay, this is name of this is aniline, right? It is reacted with nitrous acid, HNO2. This is called as a nitrous acid. And same reaction could be represented, you know, as in the reagent form as NaNO2 plus HCl. Actually, these both the reagents are same. Means over here HNO2 is in situ, means inside the reaction it should be very much freshly prepared. Okay, HNO2 should be prepared very much freshly, means inside the reaction only HNO2 is prepared. How it is prepared? If you see NaNO2, I'll just write over here, NaNO2 and HCl gives you what? HNO2 plus NaCl. So this is prepared inside. So even this and this will prepare a benzene diazonium salt. This will prepare a benzene diazonium salt. Now, you know, this is salt. You can just think of this, you know, this is a base, aniline is base, you know this, and this is what? Acid. This is a kind of a acid base reaction. You can remember, it will help you to remember this reaction. Like what do you get? You get a salt. Whenever acid and base react, what do you get? You get a salt. And what is the salt which we are getting over here? It is benzene diazonium salt, right? This process from here to here is called as diazotization. Now further, once you get this is my step 1. This is step 1. Like step 1 of a Sandmeyer's reaction. I will write over here. We'll learn Sandmeyer's reaction. Sandmeyer's reaction. This is a step 1 of Sandmeyer's reaction. So what would be a step 2 of Sandmeyer reaction? Step 2 of the Sandmeyer's reaction is this. So whatever diazonium salt you are getting over here, N2 plus Cl minus. Now this is N2 plus. This bond is very weak. This bond is very, very weak. It is just waiting to break. Okay. What you do? Since we want Br at the benzene, we write CuBr or Cu2Br2. Okay. So here also note the temperature. Here it is 273 to 278 Kelvin. This is the temperature which you should know. And here the substitution of the Br is going to take place very easily. Byproducts will be nitrogen gas and all, but here Br will get substitute. So this is what? Bromobenzene. So this is the preparation method, one of the preparation method for a haloarene. Halogen and aromatic compound. This is benzene diazonium salt. Next reaction ask is a chlorobenzene. Now this is not a preparation method. Here we are understanding how chlorobenzene is going to react with the acyl halide. Okay, but the same reaction could be asked for the preparation of a chloroacetophenol. Now I'll tell you, I'll give you the idea of this. This reaction is done by this Friedel-Crafts acylation. Okay, Friedel-Crafts acylation. What do you want? You need to convert a chlorobenzene, yes, chlorobenzene to what? This chlorine and 2-chloroacetophenone. At second position, you want this. This whole reaction is a game of a Friedel-Crafts acylation. Now I'll write the reaction, Friedel-Crafts acylation. This is chlorobenzene, this is a chlorobenzene, and you react acyl, like you want this part, CH3 C double bond O, you will take that acyl part, like this is acyl part, acyl halide, or this is also called as a acid halide, like acid halide, chlorine is connected over here. Now this in the presence of anhydrous AlCl3. Okay, so this is the thing, and the product what you are going to get over here is this. Okay, now first we'll understand what is this reaction. This reaction, make a point of this. This is electrophilic substitution on benzene, right? Here certain electrophile will be generated that will be substituted on benzene. Since there is a group present on this, chlorine will direct an incoming electrophile to what position? Orthopara. That is the nature of a orthopara directing. There are reasons for that, but that is because of the resonance, it creates a negative charge densities here, here and here, ortho and para. So that's why chlorine is a orthopara directing group. So over here, chlorine is ortho and para directing to incoming electrophile, it will direct to this position, right? These are the two important points regarding this. Now how the electrophile is generated? Question is how electrophile is generated. Electrophile is generated over here. So step one, I'll write over here, step one is this. You take this acid chloride or acyl chloride, okay, reaction with AlCl3. You are reacting this with AlCl3. Now, what is the nature of AlCl3? Okay, I will write this in this point only. AlCl3 acts as Lewis acid. Now you find the definition of Lewis acid. Okay, what is Lewis acid is doing? In short, it accepts the electron pair. It is in the need of the electron pair because octet is not complete. 2Cl, 3Cl are connected to this, right? So this reaction will take place. And what do you get? What do you get is AlCl4 minus and CH3 C double bond O plus. This is the electrophile which is generated. This is my step one. Okay, I'll clean this part. Okay, make a note of this. What would be a step 2? Step 2 is this. This is a chlorine. Okay, chlorobenzene. This is a chlorobenzene. It will get substitute. I'll not show all the intermediate step, but I'll just show. This is the electron rich. It is attacking over here. There is a hydrogen and that goes to maintain the aromaticity. Many things are there, but this is how I am showing. This is one product you will be getting. Not of course a major product. This is a minor product, and major product is this. C double bond O CH3. 4-chloro or para product is major because repulsion is less. Here repulsion is more. But since the question is 2-chloroacetophenone, you can use this reaction. So this name is 2-chloro acetophenone, right? So it is that simple. So you have to remember this. These are the many things about that reaction I have told you. So here, this reaction, write the products form. When chlorobenzene undergoes nitration. You know what is a nitration? Okay, nitration of chlorobenzene. I'll write the reaction. You know this. It is there in NCERT. Reaction is written this way. A chlorobenzene is there. You put HNO3, right, in the presence of concentrated H2SO4, and the products what you get are two products this way, chlorine and nitro over here. This is a major product. This is called as 4-chloro nitro benzene plus this is 2-chloro nitro benzene. This is the reaction. Now over here again, this is also electrophile. That is, electrophile means what? Electron deficient. No, electrophilic substitution. This is also electrophilic substitution on benzene. Okay, now what is the electrophile? Electrophile over here is, what is the electrophile? Electrophile. Okay, this is the first point. You can consider this as the first point about this reaction. Second point is electrophile. Electrophile is NO2 plus. Electrophile is NO2 plus. How it is generated? I'll write over here. I'll write step 1. Step 1 I am writing. HNO3. HNO3, how do we write? HO. Right? This is what a HNO3 structure is. Now over here, this is HNO3. So because of the H plus, this is H plus from where? From H2SO4. H2SO4 is a strong acid. What happens? There is a donation, or there is a new bond which is formed. So over here, this is oxygen. This is hydrogen, new bond which is formed. This is nitrogen, oxygen, O minus. There is a positive charge. And what happens? Positive charge on oxygen is not stable. Remember, positive charge on electronegative element is not stable. So this bond will break. While breaking this bond, what happens is that nitrogen, double bonded oxygen, minus, O minus is there. Already there is a positive charge. There will be one more positive charge. This electron is gone. One of the nitrogen is losing its electron over here. Already it is having positive charge. So it will have +2 of charge now. So overall +2 and -1 is how much? +2 and -1 is +1. So this is called as NO2 plus. This is step 1. And what is the step 2? I'll write here. Step 2. This is your chlorobenzene. This is your chlorobenzene. It will direct an incoming electrophile to what? Either ortho or at para position. So I'll write it this way. So this is your electrophile. So NO2, minor product, or we'll write major product first, and a minor product. You know, some students ask me that day, sir, only one NO2 is there. How it is possible? Two products, only one NO2 and one Cl minus. Remember, student, that is one NO2 means what? Not only one molecule is reacting. In one bottle, like water you are considering, one bottle of water is there, or 100 ml of water is there. There is not just one water molecule, large number of water molecules. Let's, for example, consider there are 1 lakh NO2 molecule in a given solution. 1 lakh, there will be more than that, but just I am considering 1 lakh NO2 molecule and 1 lakh of this, right? So what will happen in that case? 90,000 will be getting converted to this, and 10,000 will be getting converted to this product. That is what it means. Okay, so this is major product and this is minor product. We'll write over here. This is major and this is minor. Now this question, why para-chlorobenzene has a higher melting point than that of ortho and meta? Means para-chlorobenzene is this. The claim is this para-dichlorobenzene. Okay, para-chlorobenzene has higher melting point than these two, Cl ortho and Cl and Cl. So this is ortho, no? Ortho position. This is ortho. This is meta. And this is para. So para, like isomer, same molecular formula, different structural formula. That is what the isomer means. Means para-dichlorobenzene has higher melting point. The reason is that because of symmetry, packing efficiency is high. Packing efficiency is high. If packing efficiency is high, higher intermolecular forces, higher magnitude, therefore higher magnitude of intermolecular forces. This leads to higher melting point. Higher melting point. It is simple. So this increases the melting point. Question is, chlorobenzene is extremely less reactive towards a nucleophilic substitution reaction. Give reason. Means what they mean to say is that you take a chlorobenzene and you put NaOH, right? Aqueous. What they mean to say is that a substitution, the OH minus, right? This is the source of what? Source of OH minus. Means this OH minus will not substitute on a benzene very easily, or the reactivity is very less. Like if you consider the other substitution we have learned, like SN1, if you consider this SN1 or SN2, let's say this is haloalkane, right? This is haloarene, this is haloalkane. Here the substitution is very easy. Means you take NaOH, aqueous. What happens is that we get an alcohol very easily, but not over here. See, for this substitution, we need to break this bond. For the substitution to happen, the chlorobenzene bond which is there, chlorine and a carbon bond, this should be broken very easily. Remember, because of the conjugation, this will show resonance. And what we can say is that because of the resonance, Cl plus chlorine is losing its electron, this is negative charge, and this resonance will continue. I will not draw whole resonance structure, but what you can see is that there is a double bond character which is formed. Because of this resonance structure, there is a partial double bond character. Okay, and double bonds are what? Difficult to break. But same thing, if you see over here, there are electrons, but there is no any conjugation, right? For the conjugation to happen, there should be a pi sigma lone pair, pi sigma pi sigma free radical, this kind of things. But here it is pi sigma and nothing over here. Again it is sigma. So there is no resonance. Here there is resonance taking place. So what is the reason is that due to delocalization of lone electron pairs on halide in haloarene. In this case, they have asked about a chlorine. So on chlorine atom in chlorobenzene, benzene. Due to delocalization of lone electron pair on chlorine atom in chlorobenzene, there is development of partial, I'll clean this up, partial double bond character. Due to delocalization of the lone electron pair on a chlorine atom in a chlorobenzene, there is development of the partial double bond character between carbon and chlorine, right? And double bonds are difficult to break. Double bond and double bonds are difficult to break, right? Therefore, nucleophilic substitution on haloarene is very less reactive. Hope this is coming into the frame. Yes. So this is the whole reason for this. Next question is convert chlorobenzene to biphenyl. How will convert? Means they are asking a chlorobenzene, you need to take a chlorobenzene and we need to convert this to this biphenyl. Okay, this is biphenyl. This answer for this is a fatigue reaction. It is fatigue reaction. Answer for this is fatigue reaction. Means you take a chlorobenzene like this. In NCERT it is shown nicely this way. Chlorine. Okay, in the presence of dry ether, what do you get is phenyl connected to phenyl plus NaCl. We'll balance this. Okay, or it could be also shown in exam, two chlorobenzene like this and then sodium and dry ether. Okay, don't look exactly for this picture in an exam. It may be this also. Okay, they may ask, same question could be asked this way, write the products, or same question is asked, convert a chlorobenzene to biphenyl. So understand, while learning organic reactions, you need to practice a lot. You have to take different sets of questions, different ways the questions are asked. That is how we learn organic. That is one of the methods to learn organic chemistry. You cannot be like, okay, I have by-hearted this general reaction, I have written this 10 times, I know what is a Woods reaction or what is a fatigue reaction or what is Woods fatigue reaction. I know this, okay, R and R getting connected or phenyl and phenyl getting connected. So this is not going to help you a lot. Just make sure that have you solved enough examples on the particular reaction. Okay, because one reaction could be asked in a different manner. The way of asking the question may be different. Answer is same, right? Reaction is this, but the question could be like here. Question is asked: convert a chlorobenzene to biphenyl, or they may give you this reaction and identify the product, or they may not write this, but they may write this and tell you to identify the reactant. Different ways are there. Okay, like this you can do very easily. The other way also you can do. But whenever it is written chlorobenzene to biphenyl, we cannot do a reaction. Chlorobenzene to biphenyl. This conversion, this reaction, I am not remembering. Yadus jayna aplyak. For that reason, I want you to practice more example, different ways a particular example, particular question can be asked. That will lead to the perfection in organic chemistry. So I'll end the revision of haloalkanes, haloarenes over here. Thank you so much.